Welcome to this video. I thought it would be time to have a look at something which is not related to one of the ongoing series right now, but something which I see being asked rather often in the comments and questions on Udemy everywhere. A common source of errors, the difference between primitive and reference types in JavaScript. Now, what is both and how does it work? That is what we'll take a look at in this video, and that might explain why the last time you copied a JavaScript object and then changed it somewhere else, your copied object was messed up too. So let's have a look at what these are and how they work. As I just said, we have primitive values and we got reference values or types in JavaScript. You might be aware that JavaScript is a dynamically typed language and we don't have strong typings, which mean we don't define types at the point of time we declare a variable. We just have var name equals and then some value, a string for example. But we do have these types, we do have strings, we do have numbers. We just don't explicitly declare which type of values a variable may hold. But we do have types. And primitive values or types are strings, booleans, numbers, undefined null, and if we also count ES6 in, also the symbol. Now these are primitive types. And what does that mean? How do primitive types work? Let's take a closer look before we have a look at reference values. To take a closer look, I'm simply on jsbin.com and I made sure that I only have the JavaScript and the developer console open. Now let's have a look at such a very simple type. I'm going to create a new variable with the var keyword, so I'm using ES5 here, and I'll name it name, and I want to store my name in there, Max. Now of course if I log name to the console, and we can log it either by hitting run here or simply hitting Control and Enter, we see Max, and that shouldn't be too surprising. Now, if I create a new variable, second name, and I assign name as a value, what do you expect to see if I now print second name? Well, let's find out by hitting Control Enter, or first let's clear it. Now it's run. Well, we see Max twice now. For both console logs, we see Max. And that makes sense. We assigned name as a value for second name. And since name was Max, second name also is Max. This is kind of what we would have expected, right? Now it becomes interesting if we change name here to, let's say, Chris. Now, if we log second name again, what do you expect to see? Keep in mind, second name is assigned name as a value. So name is assigned as a value for second name, I should say. Now we changed name and now I do log second name to the console. What do you expect to see here? Well, let's clear and then hit run. We see Max 3 times. So even though I changed name to Chris, since I log second name here, second name still is Max. Because, and that's the super important thing, a string, and name just is of type string since we assign a string, is a primitive value. And primitive values are copied by value, you could say. So if I assign name as a value for second name, it actually just takes the content of name, the value, Max, and copies it and kind of pastes it as a value for second name. So now we have two names which at this point of time are equal in our memory. And when I reassign name to Chris, well then only one of these two things in memory is Chris. The other one, second name, still is Max. That was a lot of talking about something which probably was obvious to you. But it is important to understand this to understand what reference types are and how they work. I will show you how reference type work before we go on to the slide. Let's create a new variable here. I will name it person, and this will be a JavaScript object. Now this object may have an age, let's say 28, and it may also have a name property, which is not related to this name variable here at all. That name property could also be Max. And of course we could also have more properties here, like hobbies, which could be an array, and this array could hold sports and cooking maybe. Now if I log that person here, let's see what happens if I clear and hit run, well, we see the object with hobbies, name, and so on. So we simply log what we created here. Not that amazing. Let's create a new variable, second person, and let's assign person as a value. Let's now log second person, so this new variable, to the console. If I clear this and hit run, we see this being logged too. So this statement here stems from this console log statement, and it clearly is the same person we created here. No wonder, because we copied it, right? We assigned the value of person as a value to second person, and therefore, as we already learned up there with Chris and Max, we copied the value. So here's the thing we should expect. If I change the name of the person, so of this original object here, to Chris now, and now I again log second person. Following the logic we saw up here for the name, which was a string, we would now expect to still see our original object where the name is Max. Now, since I'm talking like this, you can probably imagine that if I hit run now, well, we see a new object with Chris instead of Max. Now keep in mind, we changed the name of person, not of second person. And I do log second person here, not person, so I do log the object which wasn't changed. And yet, we see the changed name. So what's happening here? Well, that simply happens because objects in JavaScript, just like arrays, which basically are objects, are reference types. Let's take a closer look. This is where we left the slide with our primitive values. Now, before we come to the reference values, it's important to understand where the primitive values are stored, where the actual data is stored. It has to be stored somewhere in our memory, and it is stored on the stack. Now, the stack, as the name implies, simply is a stack of data, you could say, in your memory. And this is a type of memory which can be accessed really quick and which is very limited too. It doesn't hold that much information, it doesn't have that much space. But due to the nature it is built or due to how it works, it is very fast. Now, reference types, objects, and as I said, arrays, which again are just objects kind of, are stored on the heap. Now, the heap is a different kind of place in memory. Unlike the stack, the heap takes a little bit longer to be accessed, but therefore it is able to hold much more information. It's not as short-living as the stack, you could say. And this type of memory is perfect for bigger amounts of data, or data which changes frequently or dynamically. So that's the stack and the heap. And it is this memory management which kind of dictates the behavior we saw before in the console. Let's understand how the stack works. The stack holds, as the name implies, a stack of data. Let's say we already have some random number and some random text in there. Now we create a new variable, first name, Max. Therefore, we store this string Max somewhere in memory, or not somewhere, actually on top of the stack. And we basically know that this variable, well, is accessing this part of the stack, this entry. Now, if we assign this first name variable as a value to a new variable, let's name it full name, then a new entry is pushed on top of the stack. And we know that this variable is referring to the topmost entry now. So this is how we manage the stack, or how data gets managed on the stack. We do have our different data pieces, and our variables know which position in the stack they are referring to, you could say. And remember, the stack is limited in space, and therefore it is perfect for, well, that's where the name comes from, primitive values like strings, numbers, which aren't too complex, which don't take up too much space. Let's take a look at the heap. The heap works like this. The green part is the heap. That's a place in memory where elements are not stored on top of each other. It's not managed like a stack. It's managed randomly, you could say, but therefore each element has its own address. And we still have the stack, of course. It's not an either-or solution. We have different types of memory which are able to work together, as you will see. If we now create a new object, the employee1, which is an object, the following happens. An element is created in the heap, which stores the actual object, but we do have a pointer on the stack which stores the reference, the address to this object in the heap. And the variable simply stores the pointer. And that's the interesting thing. The variable doesn't know the address of the place in memory where our object is stored. That's the difference to the previous approach. But the variable knows where the pointer lies on the stack. It knows the position of the pointer on the stack, and the pointer in turn simply stores the address of the object in the heap. Now, if we create a new variable, employee2, and we store employee1 as a value, this creates a new pointer on the stack, but, and that is now the key thing, this pointer points to the same place in memory as the first pointer did. So therefore, unlike the previous example where we managed primitive types on the stack, if we assign the value to a new variable, the actual value, the object here, is not copied. The object still is the same, it's only one place in memory. But we do get a new pointer pointing to the same place. And it's two different pointers which are stored in two different variables, but pointing to the same value. Now if we go back to JSBin, this is what explains why we see Chris here. Because when we assign person as a value to second person, the only thing we copied was the pointer, but we still only had one place in memory. Therefore, if I change this place in memory or change something about it, the name here, this gets changed for all the objects, all the variables pointing to that place. Therefore, also second person. And I hope this is clear now why in this case, when working with objects, and again, the same is true for arrays, if we change it in one place, it gets changed everywhere and every variable which points to the same place. Whereas when we work with primitive types, strings, booleans, and so on, we get real copies. Now here are two important things I want to highlight. If we create a new variable, let's name it third person because I'm very creative. And this actually has the same value as the first person here. So I just copied the object here in code. And I could have typed that manually, of course. And we now log third person here and clear this and hit run. The third person still has max. And this is even true if I were to change or were to create that right after the first person here. So third person is created right after the first person here is created. And then we change the name of person. And if I now hit clear and run again, third person still has a name of Max. And that's important. This, of course, is a different place in memory because, yeah, technically we know it. It's the same object that does hold the same values. But from a technical perspective, if you understand how code works, that it gets executed at runtime, of course your computer, your browser, doesn't know that these objects do hold the same content. And even if the browser would recognize that, it would still create two different objects at two different places on the heap because we're not copying any pointers here. We have a brand new object. So whenever we create a new object or a new array, be that with the object literal notation like here, with the curly braces, or with the new keyword, we get a new place in heap. It's only that when we assign values like here, where we store an old variable in a new one, that we copy the pointer. If we create a new object as here, it always gets a new place in the heap. So that's important to understand. Just because it looks identical here, it doesn't make it identical. Still, two different objects, two different places in the heap. That's the first important extra takeaway I wanted to add. The other one is, what if you really wanted to copy an object? So here, where we have person.name equals Chris, and then we influenced our second person because we assigned it here. What if we really wanted to copy the person object here? Well, we can do this by setting second person, and I'm just going to comment this out here so that we have a brand new variable assignment. So I can set second person equal to person to copy the pointer as you learned it. But if you want to create a brand new object, you can do this with the built-in JavaScript object, and there the assign method, which takes two arguments. The first one is an empty object. The second one is the one you want to copy. That's a little trick. Object assign is a built-in method provided by JavaScript, which allows you to create a new object and merge it with an existing one. Actually, object assign allows you to merge two objects into the first one. And here, since I pass an empty object as the first argument, which is the to be merged in object, it creates a new one, this one, and merges the person object into it. So it basically takes all the properties of the person object and merges it into second person. Now, if we do this and we hit run, you see that we got max all over the place, because now the fact that we overwrite the name in the original person object doesn't influence second person, because due to using object assign, we really copied it. We created a new object and then copied the properties of the old one. There still is a gotcha here. You see that hobbies array in our object? Now, if I not only change the name here, person.name, but I also change the hobbies, let's say I push a new hobby on this array, reading maybe. If I now hit clear and then run, now you see that it again got changed here. So here, we're logging second person, we again see that we got reading in this array, even though I just told you that we now created a new object and copied all the properties. And that is the issue. Remember that I told you that arrays are also reference types? Object assign doesn't create a deep clone. It doesn't create new objects of the properties. It just creates a new object and copies the existing properties. Now, since hobbies is an array and an array is a reference type, it didn't create a new array and merge the old array into it. It just took the old array, so it took the pointer to the old array, and merged that into our new object. So even though we have a new object, the properties, if they are reference types, still are the old ones, so we still have the old array in the new object. It's really getting confusing now, right? But I hope that this still makes sense. Arrays are reference types, so even though we created a real copy of the object, we didn't create one of the arrays element here, the arrays property. Now, there is no super trivial solution to that. There are, of course, workarounds. You could manually copy all the properties. You could use a third-party library like Lodash, which offers you a clone deep function, which does just that. It allows you to deeply clone a value, which means clone not just the object and then copy the properties, but also really clone the properties to create new properties. You could do that, and a link can be found in the video description. But it's super important to be aware of this behavior. And oftentimes it might not be an issue. If it is, well, have a look at Lodash, for example, to find a quick and easy solution to that. Almost done. One last thing. What if you wanted to copy an array in a, way of creating a real copy? Just like with object assign for an object, how would you do that for an array? Well, if you wanted to do that, let me do that here at the very end. Let's say we have a new variable, my hobbies. Then you could say equals person hobbies, and that would be, just copying the pointer, right? The issue we already know. So if I now log my hobbies here and I hit run, we see sports, cooking, and reading, but we'll see the very same thing if I do this before pushing the new value on person.hobbies. So if it wouldn't create a pointer, if it would really create a real copy, we would expect to not see reading, because we copy person hobbies before we push reading on it. But of course, what you will see is that if we hit run, we see reading on the array, again, because it is a reference type. Now, if we want to copy the real array, we could do this, for example, by using slice. The slice method is a built-in method offered by JavaScript, which allows us to take a slice of the array, and if you don't pass any arguments, it will just take the full array, and will create a new array based on that slice. So it will create a new array, and again, since I don't pass any arguments, take all the elements of the old array and put them into the new one. Therefore, if we now clear this a final time and hit run again, now we only see sports and cooking because we copied the array before we pushed reading on it. We created a real copy and not just copied the pointer. And therefore, now we have the array as it looked like at the point of time we did copy it. Your head's probably steaming now. A lot of copying around, a lot of console log statements. Still, I hope my point was clear. about the difference of reference and primitive types, how you copy only the pointer if you assign a value which is a reference type, and how you can still force the behavior of copying, well, making a real copy, creating a new object or array with object assign or slice. And then again, still with the issue of not having a deep copy in the case of both ways, actually, slice and object assign, which can be fixed with, for example, libraries like Lodash. That's a little video about primitive and reference types, and I hope it was helpful and could clear up some of the confusion and hopefully at least point you in the right direction of fixing this issue the next time you encounter some strange behavior when passing objects or arrays around in your code.